Hello everyone. Up till now, we have discussed about the basics of CAE, the graphical user interface of Ansys Workbench, how to create a model or an assembly in Ansys Workbench Design Modeler, and we have also understood how to perform the meshing on the designs. We have also understood some of the advanced meshing techniques that can be performed in Ansys Workbench. Now we will start discussing about the different types of analysis that can be performed in Ansys Workbench. The first type that we are going to understand is structural analysis. So let us start with it. Structural analysis is the most common applications in FEA. The word structure does not only come in civil engineering to refer structures like bridges and buildings, but it can also be used for the mechanical structures like machine housing, aircraft structures, pistons, and many other mechanical components. There are different types of structural analysis, and they are static analysis, dynamic analysis, spectrum analysis, buckling analysis, explicit dynamic analysis. The dynamic analysis is further divided into modal analysis, harmonic analysis, and transient dynamic analysis. Out of this, we are only going to discuss about the static analysis, modal analysis, buckling analysis. These are the types that we are going to study in our syllabus. Now let us discuss about these individual analysis. First, we will talk about static analysis. Static analysis is used to determine outputs like displacements, stresses, strains, reaction forces under static loading conditions. Static loading condition means that the load applied does not vary with respect to time, and therefore it is a gradual load. That means the load that you apply is a gradual load with respect to time. It is not an impact load. Okay, so this is the graph if you plot for the force with respect to time. And whenever you consider static analysis, there are two types of analysis that can be performed. That is linear analysis and non-linear analysis. Both the analysis can be performed. But here, in our syllabus, we are only going to cover the linear analysis. Now, when you talk about linear analysis, the analysis is going to be performed within the elastic limits, where it is obeying the Hooke's law. That means the stress and the strain have a linear graph. Okay, and therefore it follows the Hooke's law. So whenever you apply a force, suppose we have a cantilever beam over here and you are applying some force on it, because of which there will be some change in length. So now, if there is a change in length or if there is any deformation, if I remove the force, the deformation will vanish and it will again regain its original shape. That means the deformation is within the elastic limit. So that is what we consider in linear analysis. Another point that you should know about static analysis is that in static analysis, the inertia and the damping effects are ignored. We do not consider the inertia and damping effects when we are solving the static structural analysis. And if you want to understand the matrices that are solved in the software, this is the matrices that is solved in the software, that is K into X is equal to F. That means K is nothing but the stiffness matrix, X is nothing but the displacement matrix, and F is nothing but the load matrix. This is the same force balance equation which we considered for the numerical method when we solved a problem using the analytical method and the numerical method. So this is the same formula which we used in the numerical method. Okay, so this is what we understand about the static analysis. Now let us move to the next one, that is the dynamic analysis. In dynamic analysis, we can determine the displacements, stresses, and strains. But the major difference between static analysis and dynamic analysis is that the force that is applied on the model varies with respect to time, and it is a time-dependent load. Therefore, the loads that are applied over here can be impact loads or they can be random loads. It is not a gradual load that is applied in dynamic analysis. Even here, the system or the design that we are analyzing can be linear and can be non-linear both. The dynamic analysis is further divided into modal analysis, harmonic analysis, and transient dynamic analysis. Modal analysis is nothing but it is used to calculate the natural frequency of a system and also the mode shapes of the system. So in modal analysis, it is, in simpler words, you can call this as vibration analysis. In vibration analysis, you are going to calculate the natural frequency of the system. Harmonic analysis is used to determine the response of a structure. That means you will try to understand how does a system react to the inputs that you are giving. Now the inputs that you give are harmonically time varying loads. Okay, so they can be loads like a sinusoidal wave, which is a time varying load, and you want to understand the reaction of your system to these loads. So that is nothing but a harmonic analysis. And then we have something called as transient dynamic analysis. In transient dynamic analysis, we use this type of analysis to understand the response of a structure to arbitrarily time-dependent loads. Now here, the loads that we are going to apply are going to be time-dependent, but they are not a sinusoidal wave as it is in the harmonic analysis. Okay. Now when you talk about dynamic analysis, in this analysis also, we have some matrices that are solved. Now the equation that is solved in dynamic analysis is nothing but, if you can see over here, mx plus kx is equal to 0. Now this equation will be used when the system that you are analyzing does not have any external load acting on it. So the equation is m double derivative of x plus k single derivative of x is equal to 0. But if the system that you are analyzing has an external force acting on it, then the equation or the matrices that is solved by the software is m double derivative of x plus k single derivative of x is equal to f of x, where m is the mass matrix, k is the stiffness matrix, x is the displacement matrix, and f is the load matrix. Now this equation is a force balance equation for a dynamic system. Earlier what we saw is a force balance equation for a linear system. Okay, that is the main difference between static analysis and dynamic analysis. Next, we will go to spectrum analysis. Spectrum analysis is nothing but, this type of analysis is an extension of the modal analysis, and it is used to calculate stresses and strains due to random vibration. The best example to understand what the spectrum analysis is to study the behavior of a structure during an earthquake. Now that is the best example to understand what is spectrum analysis. Next we will talk about buckling analysis. Buckling analysis is used to calculate the buckling load or the buckling mode shape of a structure. Now what kind of a structures we need to study over here? Whenever a slender object means any object whose length is very long as compared to the cross section of the body, that is nothing but a slender structure. When these type of structures are subjected to axial compressive loads, the structure tends to buckle at a certain load value. So in buckling analysis, we have to find out at what load does the structure buckle, because it is a very important factor when you want to design. Okay, so that is what we will be doing in buckling analysis. Next we will talk about explicit dynamic analysis. Explicit dynamic analysis is only available in Ansys LS Dyna application. And this type of analysis can be used for solving complex problems and for getting faster solutions for these kind of complex problems. For example, when you fire a bullet, how will the structure behave? That is what can be analyzed in explicit dynamics. Explosions, okay, these all such kind of examples can be analyzed using the explicit dynamic analysis. Okay, now let us go further and understand how to perform static structural analysis in Ansys Workbench. So in this chapter, we will be understanding how to perform the static structural analysis. We will understand how to perform a complete procedure of creating the model, meshing the model, applying the boundary conditions, setting up the results, and then checking the results. When we are doing this, we will be taking all types of problems like 3D models, we will be taking 2D models, 1D models, and also assemblies. And we will also study some important tools that are related to static structural analysis. Okay, so now let us begin. The first thing that we need to do is we need to understand the graphical user interface of static structural analysis. So for starting with that, you need to add a static structural system to the project schematic window, then import a geometry or create a new geometry. So what I'm going to do over here is I will just import one geometry over here, and then I will enter into the mechanical model. So if you look at the graphical interface, we have the graphics window over here. We have the tree outline, the details window. Here you have some options like messages. You will get your graphs, tables, your report view, print view, your view triad is here. Then we have the contextual toolbar over here. The contextual toolbar changes as we select the different nodes over here. If you are in the model node, the contextual toolbar looks like this. If you are in the static structural node, the contextual toolbar changes. Okay, we have the selection filters over here. We have the viewport options over here. So this is a general graphical user interface that we will see when you enter into the static structural mechanical window. Okay. So that is the introduction of static structural analysis. Now we will go further and see how to perform analysis in static structural analysis. Okay, so now that we have understood about the static structural analysis, what it is and where it is going to be used, now we will see how to perform the static structural analysis in Ansys Workbench. For that, we are going to take the first problem, that is of an Allen wrench. Now the dimensions of the Allen wrench are mentioned over here. You can also note it down in your notebooks so that you can also practice later on. The Allen wrench, which is of size 10 millimeter across the flats, it is stopped by a means of a 100 Newton force. You can see over here, and later it is also having a downward force of 20 Newton. Okay, and we have to determine the stress intensity in the wrench under these two loading conditions. Okay, so and the material that is going to be used for this Allen wrench is structural steel. So let us go ahead and perform this analysis in Ansys Workbench. So we will come to the software. The first thing that we will do is we will add one static structural analysis system. Okay, please rename the the name of the analysis so that you know what we have done. So I will rename the analysis. Okay. Once that is done, then we will set our engineering data. So the material, we already have structural steel over here, and it is the same material that is going to be used for the Allen wrench. So I don't need to change anything over here. The next thing that we are going to do is we are going to create the geometry. Before going into the geometry, always see the type of analysis. Now the model is a 3D model, so I don't need to change the type. We are going to do a 3D analysis only. So let us enter into the geometry. Once you enter over here, you need to change your unit system. So the dimensions that are given over here are into centimeters. So I will change it into centimeters and OK. After that, create your geometry. So I have selected my plane and then I will enter into the sketching mode. I'll use a polyline. Okay. Open-ended. Dimensions. Now H1 over here is of 21 units, 21 centimeters, and V2 is of 7.5 centimeters. I'll use the constraints of coincidency. Okay. After that, I also need a fillet which is of radius 1. After setting the radius value, I'm going to apply it over here. So the design is ready. I'll come back into modeling. Now I'm going to create one more sketch on the YZ plane, sketching mode. Okay, before I come into the sketching mode, I need to set the sketch as always show so that I can see this point. YZ plane, sketching mode. Okay, so this is the point where you need to create the hexagon. So in the draw tab, we have the polygon. I need a 6-sided polygon. And I'll draw it over here. The dimensions of this polygon, you can see over here, it is 10 millimeters across the face. So I can take a dimension from this to this. Okay, you can take it as the horizontal dimension, and this is to be 10 mm. So 10 mm is nothing but 1 centimeter. The distance from here okay. Now to make sure that the center point touches over here, what we can do is we can give a dimension, horizontal dimension between this and this, and I can say that this is 7.5 centimeters. Once that is done, you can exit, and now we are going to use a sweep command. Okay, so the profile is going to be this and the path is going to be this. Okay, and now we will say generate. So this is the design that we want. You can see this is the same design that we wanted. Okay, now that means the geometry that we wanted to create is ready. So let us exit from the design modeler, and now we will enter into the mechanical window. So double click on the model cell. Once you enter into the mechanical window, see your model. Okay, now check the material, whether the model that you've created has the correct material. After that, we will go into the meshing. So now we need to generate the mesh. So first thing what we can do is we can generate the default meshing by using the update option. You can see that the meshing has been created. If you need to refine the mesh, you can change the relevance. and create a finer mesh, or else you can come into sizing and give a definite size. Okay, so I can mention over here what is the size that you want and update the meshing again. So now you can see that the meshing has been created and it is much finer. Later you can check the number of elements and nodes. You can also check the element quality. So you can see over here what is the element quality that we have got. Okay, and we have got all hexahedral elements. That is because of the shape. Because it is a uniform shape, we have got the default mesh as hexahedral. Now once the meshing has been done, we will move on to the next option of applying the boundary conditions. For applying the boundary condition, select a static structural node from the tree outline, and then you will see in the contextual toolbar you have some options like loads, supports. First thing what we are going to do is we are going to add supports. So according to the problem over here, okay, the model is going to be fixed at this end over here. Okay, so what we will do is we will apply that condition. I will come into supports. Now you can see we have different types of supports over here. Fixed support, that means all degrees of freedom will be 0. We have displacement support, that means we will only have the translation motions over here which we can control, that is X translation, Y translation and Z translation. When you talk about remote displacement, we have all 6 degrees of freedom which you can control. We have XYZ translation, XYZ rotation. So it is up to the user whether the component has to be free or it has to be fixed. Okay. Then similarly, you have many other supports that you can use. We have cylindrical support which can only be applied on cylindrical objects. It cannot be applied on planar objects. And then we have frictionless support, we have elastic support. So these are the different types of supports that we have. Similarly, we also have loads that can be applied. So now what we are going to do is we are going to take a fixed support and I'm going to add it on this face over here. Okay. Apply. Select the face on which you want to apply the support and then say apply over here. Make sure it gets added. Again go to the static structural node and then go to loads. Now according to our model, we have a 20 Newton load acting on this face and a 100 Newton load acting over here. So we will go to loads and we have pressure, hydrostatic pressure, force, remote force, bearing load, bolt pretension, moments, line pressure. Different types of loads are available. Pressure will be applied on faces, forces can be applied on lines, points, it can be applied on faces. Remote force will be a force that acts from a point. For example, it is a condition where, for example, suppose I have a plate over here, and on this plate I have a force which is acting from a certain point. It is not directly acting on the plate. There is a point at certain distance and on that particular point the force is acting. Now because of this force, even this plate is getting affected because it is connected to that point by some other means. So the force is not directly acting on the plate, but it is acting at a point which is away from the plate. So we can make use of a remote force to create a load like this. Then we have a bearing load which will be acting on cylindrical faces and will be creating a bearing load. Okay. Then we have bolt pretension, we have moments, we have line pressure which can be used for applying UDFs on 1D elements. Okay, we will be seeing how to apply this in the next examples. Okay, so let us apply a force. So I need to apply a force of 20 newtons over here. So let us create that. I'm going to select the face and then we will give the value of 20 newtons. Look at the direction of the force acting. Okay, now I need it in the opposite direction, so I will click on direction over here and you can click over here to swap the arrow directions. Once you have the correct direction, you can say apply. If you don't want to apply the forces in the vector format, you can also use the components. Okay, and you can say, now according to our view triad, it is in the y direction, so I can say there is a 20 Newton load acting, but it is acting in the negative direction, so minus 20. And now we need one more force, so I'll again go to force, and this force I need it on the line, so I'm going to select this line and I'll say it is 100 Newton, but the direction, I need to change the direction, so I'll use this line vector and then swap it. So we have the boundary condition. You can see what are the boundary conditions that we have applied. We have a fixed support over here, we have a force of 20 newtons on face B, and we have a force of 100 newtons on this edge. Okay. Now once that is done, we will go to the solution node. Now if you see, the contextual toolbar changes. We have the result option, what solutions you want from this particular analysis. So we are interested into the stress intensity. Okay, so let us go to stress, and I will be interested into the equivalent stress. Let us say if I want the total deformation that has been created. Now you take the total deformation if you want the summation of all the deformations. But if I'm only interested into the deformation in z direction or y direction, you can go to deformation, directional deformation, and then I can say in which axis. I'm interested into the deformation in y axis, plus I'm also interested into the deformation in z axis. Okay, and I'm also interested into the strain. So these are the results which I expect from this analysis. Now after that, you can click the solution node, right click and say solve, or else you can hit the solve button over here. So now the software will solve the analysis for us. So once the analysis is completed, you will see all green color tick marks appearing over here. If there are no issues and no problems in your data, you will get the solutions. Now to check the solutions, click on the node. So the equivalent stress that is generated is 138.77 megapascal. You can see the unit over here. Total deformation that is happening over here is 3.0142 mm. Directional deformation in the y-axis is 0.013105 mm, and deformation in the z-axis is 0.0033. You can see the strain value also. Now you can see the animation of the analysis. You can go to the deformation option and see the deformation. You can also see the strain. Okay, so this is the result that we got. These are the counters. You can also increase the number of counters over here, or you can reduce it as per your requirements. You can also set the viewports if you wish to. In this particular viewport, I want to see the geometry. In this particular viewport, I want to see the meshed model. Over here, I want to see the equivalent stress, and here I want to see the total deformation. Okay, so this is for setting the viewports. Okay, so this is the analysis that we've got for an Allen wrench which is subjected to a torquing load of 10 newtons and 20 newtons in the downward direction. Okay. Okay. So now in the first problem that we solved, we understood how to perform a static structural analysis by applying the boundary conditions, and how to complete the procedure of pre-processing, solving, and then post-processing also. Okay. Now in the second problem, what we are going to do is we are going to perform an analysis on a steel bracket. Okay. Now you can see over here the boundary condition that have been applied. These two holes on the bracket are fixed support. It's not clear to you, but these two holes are fixed, and there is a load or there's a pressure acting on these two holes of 30 megapascals. Okay, you can see the dimensions of the bracket over here, so that even you can create the model and practice. Okay, so you can note down the dimensions of the model. Okay, after that you can see what we have to do. So once the boundary conditions have been applied, you need to check the deformed shape of the model. We have to calculate the factor of safety, and then we also have to remodel the bracket without these fillets, and we have to see what is the change in the principal stress and the 1 Mises stress. Okay, so the first thing that we are going to do is we are going to create this model, okay, and then we will perform the analysis. So let us go to the software. So we will come to the software, and then we will add one static structural analysis system. Okay, now according to our problem, the bracket is made up of steel. So in engineering data, you need to make sure that you have the structural steel material. After which we will come to the geometry and create the geometry. Now if you have the geometry ready, which is already created in a CAD software, you can import that geometry. So in this case, what we're going to do is I will import the geometry as I've already created it. Once the geometry is imported, enter into the geometry cell. Set your unit system, and then generate the model. You can see that the model has been generated. Okay, now study the geometry. Okay, now once you get the geometry, always try to simplify the geometry wherever it is possible. Okay, that means if there is some optimization that we can do in this model, we should do it. So now if you look at the model very closely, you can see that it is a symmetrical model that we have. Symmetrical means if I cut the model into halves, it will not be it will not be wrong. Means this model is symmetrical about the zx plane, plus it is symmetrical about the yz plane. So what we can do is we can create the symmetrical model. Rather than taking the full model, I will take half of the model or 1/4 of the model. Okay, so let us create the symmetry, but before creating the symmetry, you need to see whether you have the planes. So now you can see all the planes are at the corner. I need in the center. So for that, I need to create the new planes. I will click over here, and then the original plane should be the zx plane, after which I need to transform it into the z direction. You need to know this distance. So what I'm going to do over here is I will give the value as 5, no, has to be 35 or 50. You see it is exactly in the center. Now we will say generate. So I have that plane. You can also select this edge. See, okay, this total is 35. Okay, and now let us find out the length of this. This is also 100. So from here to the center, it is going to be 50. So I'll create one more plane, which should be the YZ plane. So I needed a new plane from plane. Base plane should be the YZ plane. I need to move in the Z direction, that is this direction, and the value should again be 50 units. And we will generate a plane. Okay. Now we will come to tools, symmetry. Number of planes I need is 2. I need 2 symmetry planes. The first symmetry plane is plane number 4, and the second symmetry plane is plane number 5. And we will say generate. You can see that we have got half of the model or 1/4 of the model. Now we will take this model for analysis. So I will close my design modeler, and we will enter into the model cell. So you can see that you have entered into the model cell with the 1/4 model. Now once you come over here, first thing you need to ensure the material of the model. After which we will go into meshing and we'll create the meshing. So I will first perform the default meshing. Now you will observe that the meshing is not of good quality. So I can use the relevance options or the advanced size options or the default size. So let me give a default size of 5 mm and we will update the meshing. Okay. If you want to have finer meshing on the filleted areas or on the holes, you can refine the mesh again, or you can go for the proximity and curvature options. You can change your settings over here and you can update. So after using the proximity and curvature, you will observe that your meshing has become much more finer. Okay. Once the meshing has been done, we will come to the static structural node and then we will apply our boundary conditions. So according to the model is fixed at these two holes and there is a pressure acting at these two holes of 30 megapascal. Okay. So let us first apply the fixed support. You can see that the setting has been on the filter has been on edge, so I'll change it to face and I'll select my face. Now whenever you cut your model into half, let me explain it to you over here. Okay, imagine you have a plate with a hole. Okay, the plate is fixed over here and we have some loads acting on this face. Now because the plate is symmetrical, we can cut the plate like this and we can only take 1/4 of the section. So if I take 1/4 of the section, the model looks something like this. And I can apply my load over here. Okay. But where will you fix the model, because this area is not there in the model now. Now, whenever you create a symmetrical model, okay, you need to apply some constraints over here and over here. Why? Because practically, even if you have created 1/4 section, this area has to be considered. Okay, so the elements which are there on this face and the elements which are there on this face cannot move in this direction or this direction. That means the elements which are present over here cannot move in this direction. So what we can do is we can apply a displacement on this face and blocking this movement. Now suppose if this is your x direction and this is your y direction, then on this face I can apply a displacement saying that x movement should be blocked and y movement should be allowed. Similarly, I can select this face over here and I can say the displacement in y direction is 0. That means the elements over here cannot move in y direction. Okay. Now, because I have created a symmetric model using symmetry, you will observe that the symmetry region is available over here. So when you have created the symmetry, I don't need to worry about these constraints. But if you have created 1/4 model without using symmetry, then the displacements have to be given. Okay, please understand, if you have not used symmetry to create 1/4, you have from starting only, if you have created 1/4 of your model, then the displacement constraint has to be given. But in our situation, because we have used the symmetry, you can see the boundary condition is already applied. Symmetry region 1 and symmetry region 2. Okay, please understand this. So I don't need to apply these constraints again. Okay, next we will apply the pressure. Okay, so my fixed support is here and now I need to apply the pressure. So pressure, I will select this hole over here, this whole area over here. Okay, and then I will give the value. So the value is 30 megapascal. Okay, and the pressure is acting on the whole face. If you want to change the direction, you can also change the direction. Okay. Now there is one more thing that you need to know about forces and pressure. Whenever you are considering symmetry, I'll take the same example. Suppose the boundary condition that is acting is a force. Let us say the force is 100 Newton. Now whenever we apply a force on a face, the force will always get divided amongst the nodes that are available on this face. So if I see the side view of this, I will see something like this. I'll see a face on which we have the elements, and we will also have the nodes. So whatever force we have given gets distributed amongst the nodes. So if I cut half, or if I take 1/4, the force value will also reduce, because you are changing your area. This much area is gone now. So I don't have this much of area. So automatically what happens is the force value gets reduced. Okay. But when it is a pressure, suppose if this is a pressure, it gets applied on the entire area. So as the area gets divided, automatically the pressure will also get adjusted, and it will get applied. It will divide itself and it will get applied on this much of area. But when it is with respect to forces, forces will not get half. Forces will remain 100 Newton only, but it will get distributed only amongst this nodes. So automatically the load that is acting on these nodes will increase. But when it is pressure, pressure gets applied on the area. If area becomes half, pressure also becomes half. But that does not happen with forces. So whenever you are applying a force, and if you are going to consider 1/4 or half of this much of area, you should also divide this force by 2 if it is 2. So my force acting will be 50 newtons. Please make sure that whenever you are performing such kind of analysis, you give your boundary conditions accordingly. Okay. So now the fixed support is done, pressure is done, we have the symmetry region, and now we will add the solutions. So I need the equivalent stresses, I need the principal stresses, that is the maximum principal stress and the minimum principal stress, strains, deformations. We will solve the model. We will solve the model. After solving, we can check the results. So you can see that the stress generated inside this model is 55.087 megapascal. Total deformation is somewhere around 0.0025756 millimeters. Maximum principal stress is 33. Minimum principal stress is 0.044. Okay. In this problem, they have also mentioned that you need to calculate the factor of safety. Okay. Now, before we understand how to calculate it in Ansys Workbench, we will understand some concepts about factor of safety. Factor of safety is nothing but it is the structural capacity of a system beyond the actual loads. In other words, it is the ratio of the allowable working unit stress to the working stress. So if you check the formula, if Sm is the allowable working unit stress, that is the yield strength of a material, and Sw is the working stress, that is the calculated stress, Fs is the factor of safety. So the formula of factor of safety is Sm divided by Sw. Okay. If the calculated stress is lesser than the yield strength of the material, your design is safe. If the calculated stress is greater than the yield strength, your design is not safe. Okay. Now, factor of safety is generally calculated for materials. Now, depending on the materials, the calculations will also differ. Okay. For ductile materials, that is general metals that we use. For ductile materials, the equivalent stress is generally considered for calculating the factor of safety. So the formula is such that f of s is equal to sy divided by equivalent stress. Sy is nothing but the yield strength and your calculated stress, that is your 1 Mises stress. What is the 1 Mises stress? It is nothing but the equivalent stress. We will be studying about the equivalent stress in the coming sessions. But if the material that we are using is a brittle material, okay, the Mohr-Coulomb's theory, stress theory, is generally used for calculating the factor of safety. And this theory generally uses the ultimate tensile strength and the ultimate compressive strength for calculating the factor of safety, because the brittle materials do not have a specific yield point. Okay, because the brittle materials do not have a specific yield point, therefore we will use the ultimate tensile strength or the ultimate compressive strength for calculating the factor of safety. So if we are using a brittle material for our analysis, the factor of safety calculations will change according to this formula. So the formula is such that 1 upon factor of safety, that is f of s, is equal to sigma 1 divided by SUT plus sigma 3 plus SUC, where SUT is the ultimate tensile strength, sigma 3 is minimum principal stress, SUC is ultimate compressive strength, and sigma 1 is maximum principal stress. Okay, so let us do this now. So currently we are using structural steel material, which is a ductile material. So let me calculate the factor of safety. You can come to the stress tool over here. In tools, you can add the stress tool, and inside the stress tool you will see the factor of safety, and we can solve it. So you can see that the factor of safety is somewhere around 4.5383. Okay. So according to the formula that we have seen for ductile materials, the formula says that the factor of safety will be the yield strength of the material divided by the calculated stress. So if we check the yield strength of structural steel, it is 250 megapascals. Okay, and the equivalent stress that we have calculated is 55.087 megapascals. Okay, so if we say 250 divided by 55.087, your answer should be somewhere around 4.538. So let us see this. It's the same value that we have got. So that means the calculation that we've done is correct. Okay. Now we will understand if we are using a brittle material for our analysis, then how will we change the factor of safety calculation. So what I'm going to do over here is I will enter into engineering data, and I will add another material. Now aluminum alloy is not a brittle material, but I will consider this to be brittle, and I will apply, or I will enter the value of the compressive ultimate strength. If you see, the tensile ultimate strength is 310. I will give the same value for the compressive ultimate strength. Okay, and now we will again enter into the model. Once you enter into the model, we will change the material to aluminum alloy, which we are considering over here that it is brittle. Now after we do that, we also need to change the theory. As we discussed in the PPT, that whenever we are using a brittle material, the Mohr-Coulomb's stress theory is generally used for calculating the factor of safety. So when you click on the stress tool, you will see in the details the theory. So here, instead of equivalent stress, I am going to use the Mohr-Coulomb stress theory, and the tensile limit should be according to the tensile ultimate strength and compressive ultimate strength. Okay, and then we will again do the calculations. So if you see over here now, the stress value is almost the same, but the factor of safety has changed. Can you see over here? Previously we had got a value of 4.53. Now the factor of safety is considerably low. That means the design is not safe if you are using a brittle material. Okay. If you want, you can note down this value and you can use this formula for calculating it manually. You will see that the answers will be same. Okay. So this is how we will calculate the factor of safety for a design using different theories. Okay. So now we have understood how to do the optimization in the geometry before the analysis. What are the points to be considered if you are applying pressure or forces? What are the constraints that you should apply if you are giving or if you are considering half of the model? And how to calculate the factor of safety. Okay. Now there is one more thing that we have to do, that is we have to remodel the design without the fillet. So what I will do is I will duplicate this analysis system. Okay. Once you get the duplicate of your previous system, now in this case I need to change my geometry. So what change I want to make over here is that I want to delete the fillets. So I am going to come to create option and I will use the face delete option and select these two faces and we will say generate. So we have deleted the fillet. Okay, and then re-enter into the model. You will observe that the model has been changed. I will change my material to structural steel again. The meshing has to be regenerated because the model has changed. So I will first perform the meshing. You will see that the proximity and curvature is on because it was used in the previous system. Pressure value, fixed support, symmetry, everything remains the same. I just need to change my theory over here because again we are back into the ductile material and we will solve. Previously our stress value was 55.087. Now let us see what happens to the stresses. Okay, it is 55.4 in this area. Okay, we don't have much of a difference because the boundary condition is not acting in this area. Okay, it is not directly acting in this area. That is why I don't get any changes in this region. But you will surely see some change in the value. It has increased by some value. Similarly, the deformations, factor of safety, okay, strain principal stresses, and the minimum principal stress. So that is the analysis that we have completed for the steel bracket. And we have also understood the factor of safety concept for different materials, that is for ductile materials and for brittle materials. Okay. The one thing that we need to discuss is the equivalent stress. Equivalent stress, if you see, we have a formula to calculate the equivalent stress, and equivalent stress actually considers the it is a combination, or it is the summation of all the principal stresses that we have. So the formula is something like this. We have the equivalent stress, which is square root of the principal stresses in every direction plus sigma 2 minus sigma 3 plus sigma 3 minus sigma 1 the whole square divided by 2. So this is the formula for the one mysis stress or the equivalent stress. Okay, and these sigma 1, sigma 2 and sigma 3 are maximum principal stresses, minimum principal stresses and the middle principal stress. Okay, you can also see the same thing over here, maximum, middle, minimum. Okay, sigma 1, sigma 3, sigma 2. Okay, so this is what we have understood in the second problem. Now the next problem that we are going to study is an axisymmetric problem. Now if you remember, we have already discussed about what is axisymmetric. Whenever we have a model which is symmetric about an axis and the loads acting on the model are also symmetric about an axis, we will consider that object to be axisymmetric. Okay, so we will consider this problem now to understand how to solve an axisymmetric problem in Ansys Workbench. So the problem description is such that a long cylindrical pressure vessel of mean diameter d and wall thickness T has closed ends. It means the pressure vessel is closed at both the ends and it is subjected to an internal pressure P. Okay, determine the axial stress. Okay, axial stress and the Hooke's stress in the vessel at the mid thickness of the wall. Okay, so this is what the problem states. So we need to find out what is the axial stress and what is the Hooke's stress. Okay, the material that is going to be used for this type of analysis, it is a material that we have to create whose Young's modulus is 3E7 psi. And the Poisson's ratio is 0.3. Okay, so the mean diameter that is given is 120, thickness is 1 inch, length of the pressure vessel is 100 inches, pressure which is acting on the inside walls is 500 psi. Okay, now because we have to consider that the pressure vessel is closed from both the sides, we are going to apply one axial pressure force which is of 5654866.8 lbf. Okay, now why we are considering this? Now because it is going to be closed from both the sides, okay, we will have to apply a force. Okay, and we will calculate this force based on the pressure, okay, and the area of the circle. So this is the formula to calculate this force, which will act actually on the pressure vessel from the top, just to create the closed section condition. Okay, the other boundary conditions acting on the model is that the base of the pressure vessel, we are going to apply one frictionless support over there. Okay, so this is the model that we have to create. Okay. Now in the results, they have asked us to calculate the axial stress and the Hooke's stress for the vessel. Okay, now before we start solving this problem, let us first understand what is Hooke's stress. Okay, now whenever we have a thin walled vessel whose wall thickness is not more than 1/10 of its radius, we can calculate the Hooke's stress, and the equation for calculating that Hooke's stress is P dm divided by 2T. P is the pressure acting dm is the mean diameter, okay, which can also be calculated by outside diameter minus t, and sigma theta is nothing but the hoop stress. Okay, now if you look at the diagram, the hoop stress generally acts in the radial direction. Now please understand over here, axial stress is the normal stress parallel to the axis of cylindrical symmetry. So if this is your pressure vessel and this is the central axis, the stress which is in the normal direction, okay, will be the axial stress. Okay. Then radial stress is the stress in the directions coplanar with but perpendicular to the symmetry axis. Okay. So now if you consider this is your pressure vessel, if you consider this point, okay, the pressure or the stress which is acting in the radial direction, okay, will be the radial stress, and this stress over here which is acting in the tangential direction, or it is also called as the azimuth direction, will be the hoop stress. So if you look at this diagram, you will see sigma A will be the longitudinal stress or the axial stress, sigma R will be the radial stress, and sigma C is the hoops stress. Okay. So we have understood how to calculate what is the formula for calculating the hoop stress and what is the hoop stress and how does it act. Okay. So now let us go and solve this particular problem. So I'm going to create one static structural system. Now let me call this as axis symmetric model. Okay. I will have to enter into the engineering data because I need to create a new material. Okay, let us call this as material 1, enter, and then we need to add the material properties. So I need the Young's modulus. So Young's modulus is in PSI. Okay, as per the data, see the data over here, it is 7 e raised to 7 psi and the Poisson's ratio is 0.3. So 3e7 and the Poisson's ratio is 0.3. So depending on that, the other values are getting calculated. Okay, we will return to the project. Now let us create the geometry. So we will double click on the geometry. The unit system that I have to use is inches. So once you enter into the geometry, you will set your unit system. So change the unit system to inches. Okay, and now create the geometry. So we will click over here, enter into the sketching tab. Now I'm going to create one rectangle over here. Okay. And let us give the dimensions. And click on the horizontal dimension. Okay. Fine. Now change the dimensions. So H2 has to be 1 inch, V1 has to be 100, and this has to be 60. So you can see that it is a very thin walled pressure vessel that we have. Okay, right. So the model is ready. Now I am going to create revolved object. Okay, the axis is this. But because it is going to be an axis symmetric problem, we can only create this cross section. We can only create this cross section and take it into analysis. But for that, you need to be very sure that before starting the analysis, okay, I will add one more. Okay. I'll just repeat the procedure again. While you are entering into the geometry, you need to make sure that you set your units. You need to set your type of analysis as 2D. Please make sure that you make this change if you are going to solve a axisymmetric problem. After that, enter into the geometry and create your model. This is a major change which you need to take care. If you don't do that, you will not be able to solve your problem. So again, we'll have to go and create the model again. Dimensions, then thickness. So this has to be 100, this has to be 1 inch, and this over here has to be 60. So 120 is the mean diameter, so I am taking this to be 60. After that, because we have to solve it as an axisymmetric problem, I am not going to create the revolved body, but I'll come into concept and I'll say surfaces from sketches and create a surface. Okay. So we are going to use this model for my analysis. Okay. So exit and now enter into the model. After you enter into the model, so you need to click on the geometry, and in the once you click on the geometry, in the details view you will see one option over here, 2D behavior. So as we discussed earlier, we have different types of problem: plane stress, plane strain, and axisymmetric. So change it to axisymmetric problem. Okay, this is the first thing that you will change, after which I need to change my material. So we have created one material mat 1, I will apply that. Then carry on with your general procedure, mesh the model first. So we have used the default mesh settings to create the meshing. If you wish, you can change the settings over here. After that, click on the static structural node and apply the boundary conditions. So according to the problem, I have to apply one frictionless support on the base edge, which has been done, and then I need to apply one force whose value is, you can see over here, this is the value of the force that has to be applied. So has to be on this edge. Okay, the value is, I need to change my unit system to US customary so that the unit of the force changes to LBF, and it is 5654866.8. Okay, you can see the value. After entering the value, you need to check the direction of the force. So the direction of the force has to be in the upward direction. So I will use this edge over here to give that direction or specify that direction, and we will apply this. Okay. So now the frictionless support is done, force is done, and now I need to give another pressure which will act on the inside of the walls. I'll use this edge and then enter the value. So 500 psi is the value of the pressure. So we have applied the boundary conditions in the form of frictionless support, force, and the pressure. And now we will solve it. Now in the results, we have to calculate the axial stress. Okay. So axial stress, for calculating the axial stress, we will come into stresses. And now we are going to use the normal stress which will give me stresses in a particular direction. So I'll click on normal stress. The axis I'm going to use is the y-axis for defining the actual stress. Okay, and I'm going to use the z direction for getting the hoop stress. Okay, so from here we have already understood what are the directions and how they act. So if your cross section is over here, this becomes the tangential direction and this is the radial direction. So according to the model that I have created, okay, if you look at it from this side, okay, the z direction becomes the tangential direction. That is why we will select the z direction over here. You can also take the total deformation, and now we will solve. You can wait for the analysis to finish. And now you can check the values. So the action stress we have got is 15,126 psi, and the hoop stress that we've got is somewhere around 29,750, which is close to 30,000. The total deformation that we've got is 0.054189 inches. Okay, so this is the value that we've got. You can also check the radial stress, which is in the x direction, and we can solve. So with this we will get all the three stresses, that is the axial stress, hoop stress and the radial stress. Okay, now because we have created an axis symmetric model, and if you want to see the results for the complete model, we are only considering the cross section, but if I want to view the results in a complete model, we'll have to do a few changes. Come to the project window, go to the tools options. In this, you can click on the appearance option over here, and in appearance, switch on the beta options over here. Once you switch on the beta options, again enter into your model cell. Okay, and then click on the model node over here and click on one symmetry, add one symmetry region. When you click on the symmetry region, the type should be 2D axis symmetry, and we are going to have 37 elements, where each element will have 10 degrees of rotation. And now once this change has been done, once you click on the normal stress, look at this. So you will get your answers. Can you see this? So we have created one cross section, but the results can be viewed for the complete model. So this is how you will perform an axis symmetric problem in Ansys Workbench. After finishing the axis symmetric problem, the next problem in the static structural case that we are going to solve is a static structural analysis of a lid of a plastic CD case, which is loaded in such a manner, you can see over here, it is loaded in such a manner that it will cause these tabs to break. And we are supposed to calculate the stresses and the total deformation in this model. The material properties are given over here. We have to create one new material whose Poisson's ratio is 1 e raised to 6 psi. Poisson's ratio is 0.35. The force acting on these tabs over here is 5 lbfs. All the model dimensions are given over here, and they are into inches. So now let us create this model and solve it. Okay. So we will come to the Ansys Workbench project window, and And now I will add one static structural analysis system. I will rename my system. Now the first thing that I need to do over here is I need to create one new material. I will call this as mat2. Okay, and then I will add the Young's modulus, that is 1 e raised to 6 psi, and the Poisson's ratio is 0.35. Okay. After this, we will return to the project and then we will create the geometry. Now in this case, if you notice that the thickness of the geometry is very less, so I can solve this as a 2D problem and a 3D problem both. I will take this as a 3D problem only. Let us go into the design modeler. Once we are into the design modeler, set the unit system as inches because the model is into inches. And now let's start creating the model. So I will take the XY plane and we will enter into sketching. Now look at the dimensions first. The length is 4.8 inches and the width is 5.6. Okay, so 4.8 and 5.6. So I create one rectangle. We will give the dimensions. H1 is 4.8, this is 5.6, and then I am going to add one symmetry constraint so that it is placed symmetrically. Okay, modeling. The thickness, if you see, it is 0.3 inches. So we will extrude this model. The depth is only 0.3 inches, right? So this is the model that we have. Okay. Now what we will do is, we will create a cutout over here. Okay. We will create a cutout. The thickness of the model is 0.05. Okay. So I will come back over here. I'll select this face and go into sketching. Once we come over here, I'm going to draw one rectangle whose dimensions are this is 0.5, H3 is 0.05, and this over here is we've drawn it in the wrong direction. I will just change the sketch. Let me delete this. Okay. I have to create the sketch in this direction. Dimensions. This, and one vertical dimension over here. So this is 0.05. V6 is 4.7. And this over here is 0.5. Modeling, extrude. I need to cut the material. Once this is done, I'm going to create a shell and and I will say faces to remove. This is the face and this is the face. And the thickness should be 0.05. So this is the model that we have to create. I need to make one change over here. This face also has to be removed. So as the faces to remove this, this, and this. Okay, so this is the model. See it carefully whether you have the same model that we want. Okay, the model is ready. This is the plastic CD case that we wanted. Now after the geometry is ready, we will then enter into the mechanical model. So double click on the mechanical model. Once you come over here, the first thing that we need to do over here is that I need to change my material. Then we will mesh the model. So I'm going to use the default mesh settings for creating the meshing over here. You will observe that we've got 3D tetrahedral meshings over here. You can add one mesh method for this body, and I can try to achieve X dominant meshings, and we'll update this. We can try to achieve X dominant meshing. Now if we click over here, we've got this. We can use the relevance option to make it much more finer. Okay. Once this is done, if you feel that it is not very good quality, you can delete this X dominant option, and we can add the proximity and curvature options. Then we will update it. So now you will see that the mesh will become much more finer because of the advanced size option. It will take some time to generate because of the small element sizes. So you will observe over here that the mesh has become very fine. Okay. So because the meshing has taken a very long time to generate, it will also take a very long time to solve. So instead of using the proximity and curvature option, we will switch it off. We will switch off the proximity and curvature option, and we will use the default mesh settings. Okay. If you want to make it finer, you can use the relevance options. Okay. Or else you can give the element size, a default element size. I'll say the default element size should be of 0.2 inches or maybe of 0.1 inch. Okay, so this has become slightly finer. Okay, so once the mesh has been done, then we will apply the boundary conditions. So according to the model, we have seen that if you see in this PPT, the boundary conditions are mentioned over here. Okay. Now let us apply the same boundary conditions in the design. I'm going to apply one frictionless support on the bases over here. Now the frictionless support, when you apply a frictionless support on a face, it restricts the normal direction motion. Normal direction means, now the normal direction to this face is actually the Z direction. So this face is blocked in the Z direction, but the tangential motion, that is the tangential motion in X and in Y are available, plus the rotational and tangential direction is available. After that, I'm going to apply forces first force I'm going to apply in this on this face, and it has the value of 5 lbf, and the direction of the force, I'll use this line over here to apply the force direction. So you can see that the force has been applied. Similarly, I need to apply a similar force, same value, same magnitude, but the direction is different. So it is 5 lbf, but the direction is, swap the direction, and now we will add the results. What results do you want? I want the total deformation and the equivalent stress. Let us solve. So once you solve, you can see the results that we've got. So the stress value that we've got is 21,409 psi, and the total deformation value is 0.1 inch, which is very, very high, right? Now, we need to understand whether the result that we've got, the stress value that we've got, is accurate or not. Okay. So if you remember in the starting chapters, we have spoken about optimum mesh size. How do you decide on the optimum mesh size? Okay. Now, if you want to understand whether the results that we've got is correct or not, what do we do? Okay. We have a stress value. Now we go on refining the mesh. As you refine the mesh, the stress value will increase. But after a certain point, the stress value will almost become constant. It will not increase any further. So from this I can judge whether that this over here is the optimum mesh size. I should not further refine it because the answer is almost going to be constant. Okay. So what we will do is we will refine the mesh. Now, where exactly should I refine the mesh so that I get accurate answers? To understand that, we will add one more option, which is called as structural error. Now, first let us understand what this structural error is. Now, structural error is nothing but it is an option by which the user can understand, or they can recognize that region in the design where if the mesh is refined, the solution will become more accurate. Okay. So in this figure you can understand that after the structural error calculation, it has designated, or it has pointed out to that region which if I refine the mesh in this area, my stress solution will become more accurate. Okay. So now let us do the same thing in our case. Okay. So now if you see that if we refine the mesh in this region, our solution, our stress answer will become much more accurate. Okay. Now the refinement that we are talking about, okay, this refinement, you go on in reducing your mesh size to refine. This refinement can be done manually, or you can use an automated procedure in Ansys Workbench, which is called as convergence. Now first let us discuss about convergence. Now convergence is a tool that is available in Ansys Workbench which controls the accuracy of a solution. Okay, and convergence tool can be added or can be used in static structural analysis, modal analysis, linear buckling analysis, steady state thermal analysis, and magnetostatic analysis. Apart from this, you cannot use convergence in any other analysis system. Okay, and to use the convergence tool, you should enter a value in the allowable change criteria. You should, as a user, you should specify this value. By default, this value is always at 20%. Okay. Now let us understand how this value is used and how the convergence works. Now let us say currently we are using a mesh size of 0.5 inches. Okay, or 0.1 inches. Okay, let us say we have used 0.5 inches. At 0.5 inches, we are getting a stress value of 24,609 psi. Now from here, if I refine my mesh to 0.2 inches, I might get a solution up to 30,000 psi. This is just an example for you to understand. After that, if I further refine, you will get another solution. Okay. Now, the allowable change, suppose if the allowable change that you have given is 10%. Okay. 10%. So, in the first iteration, this is the answer. In the second iteration, this is the answer. So, if the solution, if the result in the first iteration and the second iteration, the difference in both the values is less than 10%, that means your convergence is successful. It is successful and we have got the answer. But if the allowable change, okay, if the solution that we've got is more than the allowable change, that means the difference between the two values is more than 10%, that means your convergence procedure is unsuccessful. Okay. The lesser the value you put over here, the more accurate answers you will get. But it will take more time because it will have to do more number of iterations. Okay. So now let us understand how to perform the same in Ansys Workbench. Okay. What we will do is, let us add one convergence tool. So right click on the option, means you want to do convergence for which option? For the total deformation or for the stress. So I'll select the stress and we will add one convergence tool. In the convergence tool, you need to enter the allowable change. So currently, let us say the allowable change is 20%. I will keep it at the default value, and in solution mode, you have to click the number of iterations you want. The maximum refinement loops is nothing but the iterations. Let us say we go for 2 iterations. Okay, and now we will solve. So now what the software is going to do, it will, in the first iteration, it will refine the meshing to first level, and then again it will calculate the answers. If the answer, the difference between the two solutions is lesser than 20%, it will stop, otherwise it will continue. Again it will go for the second iteration, and then again it will refine the mesh and record the answers again. So now we have to see whether the convergence procedure is successful or not. Okay, so now we see a red colored exclamation mark over here. That means the convergence process is not successful. Let us click on convergence and let us look at the graph. So the first, where we started, we had 5,731 elements and the answer that we recorded was 21,409 psi. After which, in the first iteration, the number of elements were increased to 7,845 elements and the answer increased to almost 30,000 psi, which recorded a percentage change of 33%. So the difference between the two is a 33% change. Later on, if you see, the answer has again increased and the percentage change is 30%. Now if you see, the answer is not becoming stable. Okay. The reason for this in our case is stress singularity. We are not getting a stable answer because of stress singularity. Now let us understand what is stress singularity. Now stress singularity can be major concerns in the results because of stress singularity your answers will change or they will distort considerably. Okay, and these stress singularities can be a major reason why we don't get the convergent solutions. Okay, stress singularity can happen because of many reasons. Now let us understand what these reasons are. Stress singularity can occur when you are applying constraints on points, small edges or faces with sharp corners. Okay, now look at this example over here. We have a force which is acting at this point over here. Okay, now the stress formula is force upon area. So the value of the force upon the area on which it is acting. So when you apply a force on a single point or on a sharp corner, the area is almost 0. So if I divide something by 0, the stress becomes infinite. Okay, so this is again a reason of stress singularity. Whenever you apply forces on small edges, on small areas or on points, there can be a situation of stress singularity. Okay, so you should avoid such cases. The second reason can be whenever there are sharp corners in your design. Okay, in those sharp corners your stress concentration is very high. Now what happens is whenever you go for convergence, whenever you go for refinement of meshing, these stress values will go on increasing, and what happens is in those sharp corners cracks start developing. Now these cracks will only go on increasing and the stress value will never reduce. So what we should do is we should never have sharp corners wherever the boundary conditions are acting or wherever stresses are more. You should always try to add fillets in those regions. Now according to our situation, the stress is very high in this region, right? So what we can do is we can add a fillet over here so that the cause of stress singularity is eliminated and we get correct answers. So for this I will again go back to my geometry and we will add a fillet over there. So we will come to the fixed radius option. I'll select this edge and I will select this edge. Use your control key to select both the edges and then enter the value of the fillet. Okay, if you want to reduce the fillet, I can change the value. I'll say it has to be a 0.1 radius. Now that you have entered the fillet, we will again come back to the mechanical model. Let the model get updated. Now once the model has updated, we will have to redo the meshing. So update the meshing once again. See the number of elements. Okay, and now we will perform the convergence check again. Okay, for time being you can delete the convergence. Record the stress value first. What is the first stress value that we get? You will see that the stress value is somewhere around 34,000. Initially we were getting 21,000. So now you are getting much accurate results in the first attempt itself. After that, you can see the area of structural error. So if I refine the mesh over here, you will get much more accurate results. Now we will add the convergence tool again. The allowable change is still 20%. Refinement I want 2 refinements, and now we will solve again. So previously, because it was a sharp corner, we did not get any convergence solution. Now we will see if because of adding of the fillet, will we get better solutions or not. So in the first iteration itself, if we get the allowable change is lesser than 20%, we will get an answer over there. Otherwise, it will proceed to the next iteration. Okay, now can you see that there is a green colored tick mark that appears in front of the convergence tool? That means we have got a solution. Now look at the graph changing. It has almost become stable. Okay, now can you see after the first iteration the allowable change was 23%. Okay, but in the second iteration the elements were increased from 8,398 to 16,323. And the answer that we've got is almost stable. Okay, and we've got the best possible answer for this solution, that is is 43,005 units, 5 PSI. 43,005. That is the answer that we got. So from this example, you have understood few more concepts in static structural. That is, we understood what is the structural error. After that, we understood what is the meaning of convergence and how we can use convergence. And after that, we have also understood what is stress singularity. Okay, so this is a very good example from which we have understood 3 more concepts and also how to perform the analysis. Okay. Okay. Now the next problem that we are going to take in static structural analysis is for an assembly. Now we will understand how to analyze an assembly in static structural analysis. So here we have taken an example of a C-clamp assembly. The dimensions of each and every part is mentioned over here. These are the dimensions. You can write down the values in your notebook. You can check the values. Okay. And according to these values, you can also create the same model in a CAD software. You can create the assembly. Okay, now you can see the details over here. We have 4 components in the assembly. Okay. The components are also marked over here. Okay. And after that, you can see the boundary condition data and other data for the assembly. Now, we have marked 3 phases over here, phase 1, phase 2 and phase 3. Now there are forces that is acting on phase 1 and phase 2, which is of 3000. One is acting in the upward direction and one is acting in the downward direction. So that is the force boundary condition. And then we have one boundary condition on phase 3, that is a fixed support. Okay, so phase 3 is fixed. The material properties are given over here. All the components except the pin are made up of a material called as cast steel, whose Young's modulus is 2,05,000 megapascal and Poisson's ratio is 0.265. The pin alone is made up of structural steel. Okay, so now we will analyze this. We have to apply these loads and then we have to understand what are the stresses induced in the model. So let us add this assembly. So now this assembly, I have already created this assembly in a CAD software. After that, we will first change the engineering data. We have one structural steel. We need one cast steel. Okay, we need the cast steel whose modulus has to be 20500. Okay, but make sure that you change the unit system. We have to give it is megapascal, so make that necessary change. It has to be into megapascal. So enter the Young's modulus value, make sure the units are correct. After that, enter the Poisson's ratio. It is 0.265. Okay, so same we have entered over here. Okay, after that we'll return to the project and now we will call for the geometry. So as I said, the geometry, I have already created that assembly which I am going to import now. So I have this I have the C-clamp assembly folder over here in which I have saved it. So this is my assembly. Okay, you can just check the assembly whether all the components have come correctly or not. So we will enter into the design modeler. set the unit system and generate the design. So you can see that this is my assembly which I have created. All the parts have come correctly. You can also see that the names are also there. So I don't need to rename them. Okay. Now once the assembly is updated, now we will enter into the mechanical model. So we will enter into the model cell. And now we will perform the meshing first. So let the model get updated. So once the model is updated, now we will perform the meshing. But even before we perform the meshing, we have one more thing to take care of over here, that is the contacts. So let us see the contact regions that have been created. Okay. We have one contact over here which is between the swivel and the screw over here. I will say that these two contacts have a bonded contact region. Okay. Then contact region 2, which is between the pin and the screw. I will say that they have a no separation contact, means they are free to slide. And contact region 3, which is between the screw and the C body, again I will say that it has to be no separation. That means it can slide over here. Okay. After that, I will click on meshing and I will update the meshing. So in the first case, what will happen? I will get default mesh settings for everything. Okay. Every component I'll get the default mesh setting. Okay. After which, now what we can do is we can use the sizing option for generating unique or uniform mesh size for every component. So I can say the mesh size for this is, let me change my unit system to mm over here. So in this case, my unit the element size is 4, or let us say 2 mm, and let me add one more mesh size, automatic size. I need to have a sizing control for this body. The element size should be 3. Let me update the meshing. So you will see it has become much more refined. Now we are left out with the shaft, this screw. So I will add one more sizing control. I will select this body, and even here I will set it as a 2, and we will update the mesh. So with this, we have now got proper refined mesh on every component. Okay. After this, now we will go for the boundary conditions. So as per the problem, I need to give a fixed support on this end, and I need to apply forces in this direction. On this value is 3000 Newton, and the direction has to be in the opposite direction, and the same value, same magnitude force is acting on this face, 3000, and the direction should be in the opposite direction. And after that, I would be interested into the total deformation and equivalent stress and the maximum principal stress. And now we will say solve. So even in this case, the runtime for the analysis will be quite high because we have more number of components and the meshing is also very fine. So it will take some time to solve this analysis. So now you can see we have the equivalent stress at this region, which is very high, 2908 maximum principal stress and the total deformation. Okay. So if I add one support from here, and now if I again solve this analysis, you will see that the results will differ. So now if I say that even the base is fixed, it is rested on some other support. Okay, now look at the results. So now the equivalent stress that we've got is 68.1 megapascal. The deformation is 0.01 and the maximum principal stress is 81. Okay, so did you understand how if I did not give this support, the stress value is quite high. Okay, so now this object will be rested on some other object and then we will apply this, we will be pushing down this rod. So a simultaneous resultant force, opposite reaction force will be applied over here. Okay, so with this example, now you have understood how to perform a static structural analysis on an assembly. Okay, you can also calculate the reaction forces. For reaction forces, you need to go to the probe option and you need to say that I want to calculate the reaction force and I want to see the reaction forces on fixed support. Solve it, and now you can see the values. Similarly, I want to see the reaction force for fixed support 2. You can also see both the reaction forces. Okay, so this is the reaction force. You can also see the animation. Okay, now whatever animation you see over here can be exported to a AVI file. You can write the name for this. I will say that this is reaction force. Give a saving location and save it. So the reaction force video will be recorded and you can also see this video. So that is the video. If you want it for some more time, you will have to change the time over here. Okay, I want it for 10 seconds or you can increase the number of frames and then again you can record it. Okay, or you can export it. You also have something called as the results that you get. If I want it in contour bands or smooth contours, you can see. If I say contour bands, you will see it like this, smooth contours, or they should be just iso lines or no color. These are all post-processing tools which we can use. I want to see the undeformed model as a wireframe mode. Can you see this now? Or I want to see it as model. So you can see that the undeformed model is also seen. You can see a background of your undeformed model over here. Okay. You also have something called as probes. The maximum probe and the minimum probe, which shows the location of the maximum stress value and the minimum stress value. Or else you can use a manual probe. Just click anywhere and you will see what is the value at that region. For example, I want to see what is the what is the deformation at this point, what is the deformation at this individually. Even for that, you can use it. Okay. So these are some of the post-processing tools which you can use for your result viewing. Okay. In the previous chapter, we have understood about structural analysis. We have seen how to perform a static structural analysis. We took various examples of a 3D problem, axisymmetric problems. We took an assembly. Also, we understood some important concepts related to static structural analysis like factor of safety, convergence, what is stress singularity. Okay, so we've understood some important concepts. Now the next chapter that we are going to start with is wizards and tools. Okay. Now let us first understand what is this wizards and tools, and then we will see how to work with it. So in Ansys Workbench, we have a different number of tools and wizards that are available. Now these tools and wizards are actually there to help the user to complete the analysis process. So with the help of these tools, we can complete the process by following the rules and following the steps. Okay. So when you want to use the wizards and tools in the mechanical window, you will have to click on this green colored arrow that appears there. Once you click over there, you will get one mechanical application wizard box just on the right hand side of your graphics screen, and in that you will see that there are some steps that will appear, and you just have to follow these steps to complete the process. Now in this application wizard, let us first go to the wizard. Let me go to the mechanical cell. Okay. Now here, if you see, this is the button that we are talking about. So once you come to the mechanical window, you can click over here. Once you click over here, you will see that the mechanical application wizard will open. Okay, and these are the steps which you need to follow. Now, in the mechanical application wizard, you have different wizards that we can use. We have separate wizards for stress analysis, for fatigue analysis, modal analysis, thermal analysis, magnetostatic, contact regions, for defining contact regions. Okay, so these are the different wizards which we can use for different types of analysis. Okay. So this is nothing but the wizard tools. Now to understand the wizard tool, what we will be doing is we will be taking one example of a fatigue analysis, and we will solve the fatigue analysis using the wizards and tools applications. Okay. But before we start solving the problem, first let us understand what is fatigue analysis. Now fatigue analysis is nothing but it is a progressive and localized structural damage that occurs when a material is subjected to cyclic loading. Okay, that means whenever a design or a model is subjected to cyclic loading. Cyclic loading means the load condition is in a cyclic manner. Means we are continuously loading the structure and unloading the structure. Now this situation will go on happening for a very long time. So whenever such a condition is there, fatigue will occur in that design, and we need to analyze the fatigue line. Okay. Now fatigue occurs when a material is subjected to repeated loadings and unloading. That is nothing but cyclic loading. Okay. Now when this is happening, the model starts to deform. So when you are applying the cyclic loadings on a design, the model starts to deform, and after some cycles of loadings, small cracks start developing in the design. Now these cracks then gradually start increasing, and suddenly the structure will fail. So when you start loading and unloading the design, wherever the design is weak, there cracks will start to develop. Initially they are all small cracks, but as the cyclic loading continues, these cracks will go on increasing, and then a certain point will come when the structure will fail. So in fatigue analysis, we need to understand for how many cycles the model will last or how many cycles the model will sustain. Okay, so this is what we need to calculate in fatigue analysis. Now when you talk about fatigue analysis, as we discussed, we have to calculate the fatigue life. Now what is fatigue life? Fatigue life, which is denoted by NF, it is defined as the number of stress cycles of a specified character that a specimen sustains before failure of a specified nature occurs. So it is not, in simpler words, it is nothing but it is the life cycle of a model, of a material. Okay. Now to calculate the fatigue life, there are different methods. Now the methods that we will be discussing is, we have two methods, that is uniform material law, which is also called as the UML method, and the second method is SN curve. Let us talk about the UML method first. The UML method was developed by the end of the 20th century, and this method was developed to determine the fatigue life of aluminium and titanium alloys. But later this method was also extended for other high strength steels and cast iron. This method was very easy and user friendly to use because it required only the tensile strength data of materials. So that is why it was very easy and handy method that could be used. But there was a drawback in this method, that it could be only used for high strength steels. Okay. Then the next method that we are going to talk about is SN curve. The SN curve is nothing but when the cycles are more, when the loading cycles are more, the SN curve is generally used to calculate the fatigue life of the material. The SN curve is also called as Euler's curve. It is a plot or it is a graph of stress versus the number of cycles, that is N, which is known as the SN curve. So it is actually a graph of stresses, the number of cycles. Okay. Now even the SN curve has some limitations. Now what are the limitations that occur in SN curve? That is, the SN curve is affected by conditions like corrosions, temperature, and presence of sharp corners. So because of this, even the SN curve has some limitations. Okay, and you can see over here we have an example of the SN curve for steel, and we have another example for SN curve of aluminium. Okay. Now when you talk about the SN curve, there are different theories on which the calculations of SN curve depend. Okay. Now, theories that we are going to talk about is, you can see this graph over here first, and you can see different curves A, B, C, and D. So the A plot over here is a plot of a SN curve which has been done using the Soderberg theory. Then the B plot is according to Goodman theory. C plot is according to Gerber theory, and the D plot is according to mean stress curve. Now in Ansys Workbench, you will see that the alternating stress mean stress graph or the curve is already present in every material. With the help of this graph, we will be able to calculate the fatigue analysis. But if you want to change the theories, we can also change the theories according to which we want to calculate. Okay, so you will observe this when we perform the fatigue analysis. Now we will see another thing that is important that we need to understand in fatigue analysis. As we discussed, fatigue analysis or fatigue occurs when the model is subjected to cyclic loading. Okay. Now when you talk about loadings, there are two types of loading conditions that can be studied in fatigue analysis. The first loading condition is called as a fully reversed loading condition, And the second loading condition is called as zero based loading condition, or it is also called as repeated loading. Now what is the difference between the two? If we consider that the load is a fully reversed load, then let us say my load acting is 100 Newton. So the loading condition, if it is fully reversed, if it is fully reversed, then the loading condition acts in this manner. It goes from 0 to positive side, again 0 to the negative side. It is like this. You see over here also, a fully reversed loading condition is like this. It will go to the positive side, that is 100, 0, and this is negative 100. So the loading condition will be, it will be exerting a positive force, plus while going back it will also create a negative force on the model. Okay, so this is what happens in a fully reversed loading condition. But in the other condition, which is the zero based loading or repeated loading, in zero based loading condition, the load gets applied in this manner. It only goes in the positive direction 0, it gets applied like this. It never goes to the negative side. Okay, so these are the two types of loading conditions that we need to understand. So let us just see what we've understood. What is fatigue analysis? Why are we performing it, and when we need to perform the fatigue analysis? We've also understood what is fatigue life. We've seen what are the different methods to calculate the fatigue life. We've understood the two methods, that is UML and SN curve. Then we discussed about the different theories that are used to determine or predict the SN curve. And then we have understood about the different types of loading conditions that are involved in fatigue analysis. Okay. Now we are going to solve the problem for fatigue analysis. Okay. So we are going to take an example of a 4-stroke crankshaft. Now this 4-stroke crankshaft is subjected to loads at these pins. Okay, the load value is 25,639 newtons. So over here and over here it is acting in the negative y, and over here and here it is acting in the positive y. And this will be repeated for number of cycles. So we need to understand for how many cycles this model will last. Okay, the material that we are going to be using for this analysis is aluminium alloy. Okay, and the model, we can create a crankshaft, 4-stroke crankshaft as per the design. Okay, now let us go to Ansys Workbench. Once you come over here, we will add one static structural. Now as we saw over here, we need to use aluminium alloy for this analysis. So I will click on the engineering data, we will click on the data resources, general materials, and I will add the aluminium alloy. Once that is done, check whether it has been added into the outline of schematic. Return to the project and then import your model. So let me import my design. This is my model that I am going to use. Enter into the geometry design modeler and see your design. Set the unit system and generate the model. You can see the design now. So this is the 4-stroke crankshaft that we have. Okay. Now let us go to the mechanical model. Now once you are in the mechanical model, the first thing that we need to do over here is we need to change the material. So we have to use aluminium alloy for this analysis. I have changed the material. Then we will create the mesh. Now, as we can see very clearly that we have very small areas, filleted regions. So instead of doing the default meshing, I can come for proximity and curvature, and then I will update the mesh. Now, because of the use of proximity and curvature, the meshing will take some time because it will generate fine meshing. So now you can see that the elements have been generated and we've got the meshing. Okay. The number of elements generated are 1,28,254. We can also check the element quality. We have all tetrahedral elements. These are the elements that we have generated. Okay. After that, now we will go to the next step where we will apply the loads. But for this, I am going to take the application wizard. Now see, when you come over here, you can just click on these steps. So the first step is we have to verify the material. We have already done that. After that, we need to add the number of steps. Because we are performing static structural analysis, we are going to take only one step. And whenever you perform static structural analysis, you need to remember that the run time or the analysis time is only 1 second. Then now the next step is we need to insert the loads. So once I click on this step, it also points to me where on which option can I use for inserting the loads. So I'll take the loads option and now I'm going to select the force. So now I'll select this face and this face plus this face and this face. And now the value of the force that is going to act is, you can see over here, it is 25,639. Now this force value has been calculated by some calculation using the piston dia, pin dia. Okay, there is some theory which is used to calculate the load value. Okay, so it is 25,693 newtons. And then we have to give the direction. So for direction, because I don't have a straight line in the y direction, I will resolve it using the components. And I will say it is 25,693 newtons. You can see the direction is in the upward direction. Okay. Now, again, I will apply one more load, but this time it is over here and over here. Again, I'll use the components, and this time it will be in the negative direction, so 25,693, so that they act in the downward direction. After this, I need to give the supports. So when I say insert supports, you will see the supports option. And now I'm going to fix all the surfaces. Use your control key, keep your control key pressed and start selection of the faces. So you can drag your mouse over here so that all the faces get selected. So the selection becomes very easy. Okay, you can select this also. You can go to the opposite side and select again. Make sure you don't leave any surfaces. Okay, fine. So we have selected all the faces and now I will say that they have to be fixed. So my boundary conditions are such that all these faces are fixed, and then we have loads acting. on the pins. Okay. Next, now we have to solve, but before we solve, I need to add the results. What do I want to check? So I want to check the equivalent stresses and the total deformation. And now we will say solve. So where do I need to click? So I will click over here so that we solve the analysis. So now the model will be solved and we will get our results. Because we have used the proximity and curvature option, the meshing is very fine and thus the runtime will be more. Okay, now we will click on equivalent stress to see the results. You click on total deformation to see the deformation. So as I said, the result has been scaled. If I see the true scale, you will see this is the result. So this is my deformation and this is my stresses. So the stress is 208.42 megapascal. Okay. Now I need to perform a fatigue analysis. Okay. So I am going to use the wizard, fatigue analysis wizard, for performing the fatigue analysis. Okay. So once your supports have been inserted, click on the solution tab, right click and insert a fatigue tool. Okay. Right click on the solution node, insert, add the fatigue tool. Once you add the fatigue tool, then you need to perform these steps. Okay. So the first thing is you need to add the fatigue results. What exactly do you need in the fatigue results? So I need to add the life. I need to check I need to calculate the fatigue life, fatigue damage, or factor of safety. The same thing can be done from here. Right click, insert life. Okay. So now I need to calculate the fatigue life. Okay. Now when you click on the fatigue tool, we spoke about or we discussed about the types of loadings in our in the PPT. Okay, so we have two types of loadings. So here is the type of loading that we spoke about: fully reverse and zero based loading. First, we are going to calculate the fatigue life according to fully reverse. That means the load that we have applied is 25,693 Newton. So the load will be acting in such a manner, from 25,000 it will go to 0, again to the negative side. So it will be in a cyclic manner. Okay, and you can also see the theories. We spoke about the Soderberg theory. These are the different curves. See, these are the different curves that we spoke about: curve A, curve B, curve C, and curve D. Okay. Now, before we do the fatigue analysis, there is one more important thing that we should know. Come to the project schematic window, double click on engineering data. The material that we are using is aluminium alloy. Now, as I said, every material that we have will have one alternating stress mean stress curve. Okay, and in this you can see the number of cycles and the stress value. You can see the SN curve over here. Okay, so now this will show that if the stress value is somewhere around 275 megapascal, then it will last for 17,000 cycles. But if the stress value is lesser than 82.74 megapascal, it will last for 1 e raised to 8 cycle. That means the maximum number of cycles for which this material can last. According to our analysis, the stress value that we have got is 208, okay, which is higher than the minimum stress. That means now we can see the number of cycles. Okay, so we can select live, right click, and we can say solve. And in the life you can see the minimum number of cycles. The minimum number of cycles for which this model can last is 31,069 cycles. Maximum cycles is 1 e raised to 8, which is the same thing that we understood over here. 1 e raised to 8. The minimum number of cycles is 31,069 cycles. Now this is for the fully reverse cycle. But if I change it to zero based, okay, then what is the change? Now here the life will increase. You can see now it is going to last for 1.0496 e raised to 7 cycles, because the zero based type of loading is less, it will have lesser effects, okay, as compared to the fully reversed cycle, fully reversed loading condition, okay. And you can also see the theory type, okay. I can change it to the Goodman theory. You can see the Goodman theory, Soderbergh, or according to Gerber. Same thing we can see over here also. Okay, so the theories can change over here, and then you can calculate. You can change this to fully reversed, Soderbergh theory, and solve. Okay, so you can see this is the way by which you can perform the fatigue analysis. Okay, let us just discuss this. What we have understood in this chapter. We have understood about fatigue analysis. What is the meaning of fatigue analysis? What is the meaning of fatigue life? What are the different methods by which you can calculate the fatigue life? We spoke about SN curve, and then we have seen what are the different theories on which the SN curve depends. What are the types of loading condition? And then we have taken this example. And always remember that the fully reversed type of loading will always have lesser life cycles as compared to the zero based loading. That means fully reversed loading condition is much severe as compared to the zero based loading condition. Okay, so this is how we will perform the fatigue analysis, and this is how we will use the results and tools. Now the last part over here is view report. You can click on view report over here, which will generate a complete report of your analysis. So you can come to the report preview and you can see the entire report of your analysis, which shows all the details of the analysis that we've performed. It gives the entire data. Okay, and in the end it will also show the results. The minimum life cycles is 31,069. Okay. Now in this case, this is the report that we've generated. Now this report is in an HTML format which can only be viewed in Ansys Workbench. But you have an option over here which is send to Microsoft Word or Microsoft PowerPoint. So you can export this report from Ansys Workbench to a Word format or to a PowerPoint format. Now let us say if you want to add these images, click on the geometry to come back to the geometry view. Let us say you want to add these images to the reports. So first you need to capture these images. To capture the image, first select the option, and here you will see one option over here. You can say image. So I'll click on the image option so that this image is captured. Similarly, I also want to capture the fatigue life image. So I'll click on this and I will again click on image. Now you'll see that two images have been captured. Again go to view report. Again the report is generated, and now this time the image will also be taken into account while generating the report. Now click on the graphic screen. Now again go back. See, you can see that the images have been added in the report now. Can you see this? This is how you will use your mechanical application wizard to perform the analysis, and the same wizard can be used to generate a report of your analysis. And this report that we generated can also be exported to different formats. Okay. So with this we finish how to perform fatigue analysis.